Hi, welcome to this module. In this module, we will see a different multivibrator. So, what is that different multivibrator? Different multivibrator, I mean by astable multivibrator. Okay. So, what is astable multivibrator? Right. We have seen a multivibrator that can, if I apply a positive feedback system, right, that oscillates between high state and low state to produce a continuous output, then that kind of circuit is called what? That kind of circuit is called a multivibrator. It vibrates multiple, right, multiple points like on and off, on and off, on and off, right. So, it is a astable multivibrator. Let us see in detail, do not worry about it. If you come to the slide, a multivibrator circuit is also a positive feedback system, right. It is a positive feedback system. Now, when you apply positive feedback, when you want to use the circuit as an oscillator, when you apply negative feedback, when you want to use circuit as an amplifier. So, a multivibrator circuit is also a positive feedback system. So, if it is a positive feedback system, what will happen? It will oscillate. It will oscillate between a high state and a low state to produce a continuous output. You can say high state, you can say low state, it keep oscillating high and low to produce a continuous output. Depending on how they vibrate between two states, multivibrator can be classified as astable, monostable, bistable. But if they in the case of astable multivibrator, what is that? Astable, both the states are unstable, both the states are unstable, right. So, it means for the circuit, if the circuit is at high state and since it is an unstable state, the circuit will remain in that state only for a period of time, after which it will return to the low state, right. So, and since this state is also unstable, it will again return to the high state. This process of continuously changing the high state to low state to high state, right, results in clock pulses, and thus astable multivibrator is also called free running oscillator, right. So, a multivibrator is a positive feedback system, it oscillates between high and low. If how they vibrate between two states, according to them they can be classified. We have seen bistable, how they are classified: astable, bistable, monostable, and astable are those whose states are, both states are unstable, right. So, since it switches from high to low and low to high, it results in a clock and is also called free running oscillator. They generally have a 50% duty cycle. So, the duty cycle for a astable timing pulse is 1:1. The width of pulses depends on R and C, right. Astable multivibrators are used as the clocks and the timers, right, because it continuously generates output signal with 50% duty cycle, right. It can be used as a timer, it can be used as a clock, right, and thus these astable multivibrators are used for applications such as pulse position modulation, PPM, and frequency modulation. These are the application of the astable multivibrator. So, if you see here, this is the circuit for the astable multivibrator. This is the capacitor voltage and this is the output voltage. So, what is shown? The circuit diagram for astable multivibrator using op amp and its voltage response are shown here. Astable multivibrator switching or an astable multivibrator is a switching oscillator that can be formed by adding R and C, right, as a feedback network to the Smith trigger. An astable multivibrator can be used for generating low frequency square waves. You can here see you can generate a low frequency square waves. At time t equals to 0, initially the voltage across the capacitor is 0, right. Assuming initial output voltage plus V A, thus initially the capacitor will charge through resistor R1 to plus A, right. So, voltage is plus A or plus V I said plus A, which is the output of the comparator. The capacitor, since it is at 0, it will start charging to plus A. However, the capacitor voltage reaches A by 2, the output switches to minus A. As soon as it reaches to A by 2, right, the output swings back to minus A, you see. So, from 0 it starts here, it reaches to A by 2 and the output goes to minus A. Thus, capacitor starts to discharge, so the voltage drops to minus A by 2 and the output switches back to A. So, again it starts charging to A by 2 and again output change switches to minus A. This will call capacitor voltage cycles back and forth between A by 2 minus A by 2, resembling a triangular wave, which you can see here, right, and the comparator output voltage resembles a square wave, right, because it is charged, on, discharge, off, again charged, again on, again discharge, it is off, right. So, it is like a square wave. The frequency of output square wave can be determined by analyzing the transient response of RC feedback network and the time period of the signal generated by the multivibrator is given by T equals to 2 times R1 C1 log natural log of 1 by 1 plus beta divided by 1 minus beta. So, no idealities related to comparator may affect the frequency of oscillation, right. So, you need to understand how the astable multivibrator works. Now, if you want to perform the experiment, then you have to connect the circuit as shown here, which is right over here. Select the resistance values and calculate the period of generated waveform. Observe the output voltage and voltage across capacitor. You can observe the voltage across capacitor from the oscilloscope. Compare the output frequency with the theoretical result. So, regenerative feedback factor, you see what is the peak voltage across capacitor, what is the output voltage and what is the time period of the output signal. This is the experiment that you need to perform. We will see if we can also perform the experiment to show it to you how does the astable multivibrator works. Now, to do that, the things that we have seen particularly about circuit designing, my TA Sitaram and Suman, they will also discuss about the circuit design and perform a simulation. Then they will discuss about how the circuit operates. We have seen in theory in detail, but we just need to have a quick recall of how circuit operates. So, they will show you about that circuit operation and compare it with the simulation. So, simulation we use multisim and then we do not stop at simulation, we also go further and perform experiments. So, we will compare theory with simulation, we compare theoretical results with our experimental results. So, this is the complete idea, and now what I will do is I will request Suman and Sitaram to join us and show us how the experiment procedure can be carried out. Guys, you need to focus. We have designed this thing after lot of brainstorming, and this experiments I feel that if you learn, it will be good for lot of other applications, right. So, I will request now TA to help us with the circuit experiments, and I will request him to join us.
Now, we are going to see an astable multivibrator. So, we will start with an astable multivibrator now. So, similarly to our previous modules, even in this module, we will briefly look into the design of operational amplifier as an astable multivibrator, how it works, and we will do some theoretical calculations. We will also discuss up the connection of the circuit. Once the theoretical part is done, we will design the same circuit in circuit simulation software. So, we are using multisim. So, we will use multisim live to design, and we will verify whether the theoretical output as well as the expected output is similar or not. Then the functionality we will verify it. Once that is done, we will look into the experimental connections of the same circuit in using a TI board, and we will compare the results that we are getting from experimental and simulation as well as a theoretical. So, as in theory we have already discussed, as professor has already discussed about an astable multivibrator, we will briefly look into the design, we will discuss that, and we will go back to our procedure in a similar way. Now, when we look into the astable multivibrator circuit, if you remember correctly, our inverting and non-inverting Schmitt-Trigger circuits, we can see here that one part, when you observe, it is also following similar kind of some part of design is similar to our inverting type Smith trigger, isn't it? When you observe our, when you recall our similar Smith trigger circuit, the Smith trigger circuit is using a positive feedback. Even in this case, you have a positive feedback connected with a resistance R3 and one more resistor R2. Whereas for inverting Smith trigger, the input is being connected to the negative terminal. Even in this case, forget about this R1 resistor and C1 resistor, but when you clearly observe that when we remove this R1 and C1, we can see that input is connected to the negative terminal of here. That means when you observe, even for Astable multivibrator, we require some part of our Smith trigger circuit too. Now, if you recall what we discussed in our inverter, inverting Smith trigger, we remember that the thresholds required for Smith trigger depends upon the positive VSS and negative VSS, the supply voltages of the operational amplifier, and the resistance that we are using, the feedback resistance and input resistance connected to the positive terminal of your op amp. And we have also seen the calculations like the higher threshold value, right, VTH, the higher threshold value is equal to plus beta into VSS. That means positive supply voltage into the beta, where beta is nothing but, in this case, R2 divided by R2 plus R3, right. If you recall, just look into our look into the previous module on inverting Smith trigger. So, beta is nothing but R2 by R2 plus R3, right. And we have also know that if you recall our inverting Smith trigger, when the input voltage is greater than the higher threshold, we will get minus VCC. When the input voltage is lower than lower threshold value, we will get a positive VCC. So, that means that the lower threshold value is beta into minus VSS, right, where beta is nothing but again R2 by R2 plus R3. But in case of an Astable vibrator, so we have another component like R1 and C1. So, it is a combination of R1 and C1, and the input to this RC filter is coming from the output of your op amp, isn't it? And we know that since it is a positive feedback, op amp can only be in two states, either in a positive VCC state or negative VCC state, because it always operates in plus or minus VCC state or in a saturation region, isn't it? So, because of that reason, the input applied to your RC filter. So, if I clearly write it down here, okay. So, what we will do is that here we will see this is a resistor and this is a capacitor. So, this is R1, okay. This is R1 and we are saying this is C1, and the output of op amp is being connected here. The output across the capacitor C1 is connected to the negative terminal, and we also know that the op amp input impedances are really higher. So, since those are all really higher, right. So, no current will flow, that means R1 and C1 are in series. So, how does the circuit looks like? It is nothing but our integrator or your RC charging circuit. But what is our charging of your RC filter? So, at what voltage it will charge? So, it charges up to the input applied to RC filter. In this case, the input applied to the RC filter is nothing but the output of your op amp. That means, when your output is at positive state, the capacitor will try to charge to plus VCC state, right. And again, when the output is at minus VCC state, whatever the value is stored at your capacitor will discharge to minus VCC state, or it is a negative charging of your capacitor. So, that means the capacitor will always try to charge till plus VCC, and discharges from plus VCC to minus VCC when the input of RC filter is at minus VCC. But when we see here, we also have another component like R3 and R2. Because of that reason, it creates some thresholds to our stable multivibrator. So those thresholds are nothing but your VTH, higher threshold and lower threshold value. So if we recall, what are the thresholds? The thresholds here is nothing but V reference in this case. So it depends upon the resistance value that we choose, that is nothing but beta into plus VSS and beta into minus VSS. So these are the two thresholds that we are setting. That means whenever depends upon the R3 and R2 resistors, the capacitor will charge only up to that particular value. Then since the input voltage, since the capacitor is keep on increasing, whenever the capacitor reaches the voltage of beta VSS value, when the input voltage is, that means beta VSS value is greater than our input voltage, the charging voltage of the capacitor C1 is greater than beta VSS, which is the threshold value, then the output goes to minus VCC. So here we can observe that the output is going to minus VCC. Since the output is going to minus VCC, whatever the energy being stored in our capacitor will again discharge back to minus VCC state. So we can see that it is discharging, but it is not going till minus VCC because we have another threshold at the negative side. So that threshold is minus beta VSS. So whenever the capacitor voltage is again lower than beta VSS, the output state goes to plus VCC, again starts. So this continues. So if I want to calculate the frequency of our stable multivibrator, at what frequency it is being oscillating, that entirely depends upon our beta value and VSS value, right. So as we have already seen in a theory class, how do we calculate, as a professor discussed in the theory class, how do we calculate our T value, and we also know that the relation is, the T relation is 2 into R1 C1 into log 1 plus beta by 1 minus beta, where beta is nothing but R2 by R2 plus R3. We will theoretically verify, we will also do the simulation verification along with an experimental verification too, right. So when we go to our experiment, so the same thing we are using even in the experiment. So what we are doing is, we will connect in the same fashion. So in this case, let us consider R1 as, so I will consider R1 as 1 kilo ohms. So we will consider R1 as 1 kilo ohms and C1 as 1 microfarad. So if it is a case, what is the time constant? Tau is nothing but RC. So RC meaning, so time constant RC, which is nothing but 1 kilo into 1 micro. So 1 kilo into 1 micro is how much? 10 power minus 3. That is RC value. Now, but do we require RC along with an tau component? We also know, we have to understand what is the time duration. We require to know what is this one and what is this one. The addition of these two gives us T value. Now how do we calculate that? So in order to calculate that, first we should understand the beta value and we should understand the thresholds, plus the higher threshold value and lower threshold value. So now we will see. So we will consider, in order to understand that, first we will consider different R1, R2 and R3 values. So as we have seen in the last experiment, we have considered R1 and R2 as, in one case we can consider as 10 kilo ohms. So that when I say R2 is equal to R3 is equal to 10 kilo ohms, then the beta value is nothing but 1 by 2, right. So beta is nothing but what? R2 divided by R2 plus R3, 10 divided by 20, this is 1 by 2. Now since it is 1 by 2, what is the peak voltage across a capacitor that we can see? It is nothing but one peak voltage that it is going to plus peak voltage or plus reference, right, or plus beta into VSS is nothing but 0.5 into right, 1 by 2 is 0.5 and VSS is 15 that we are using it, it is nothing but 7.5. That means we are making the capacitor to charge only till 7.5 volts, even though input voltage, the output of your op amp is nothing but the input of your RC filter is making it as 15, but because of the threshold the capacitor can only charge up to 7.5. When the capacitor is high, the capacitor in voltage, the charging value of a capacitor is greater than 7.5, it makes the stable your Smith trigger value to, it makes the op amp output to go to minus VCC. So, it starts again discharging, is not it. Now, what about minus V reference value? It is nothing but minus 7.5. So, that means the output, the capacitor voltage will always charges and discharges plus from plus 7.5 to minus 7.5 volts. That is what even we have seen, right. Now, based upon that, how do we calculate our time period? So, if we recall our basics on charging and discharging of a capacitor, if you recall our charging and discharging time constants of our capacitor. So, the charging of a capacitor, right, if I say this is my capacitor charging rate, right, this is voltage across capacitor and this is the time, right. So, if I want to know what is the time it takes, so we know the equation for this is nothing but voltage across the capacitor is the supply voltage into 1 minus e power, right, 1 minus e power minus T by RC, right. Now, but here the scenarios are little different, right. So, now what is the threshold? The threshold is we are charging only up to 7.5 volts. We are not allowing the capacitor to charge more than 7.5 volts, because when the input voltage of a capacitor is greater than 7.5, the input connected to RC filter is going to minus VCC, right. Because of that the maximum voltage is 7.5. So, I want to know what is the time taken for the capacitor to reach from 0 to 7.5 volts, right, from 0 to, so 0 to 7.5 volts. Now, when I say 0 to 7.5 volts, right. So, what is now what like how do we calculate, how do we get a time value? So, that means we should understand the T. So, what we are trying to find out now is what is the time duration from here to here, let us say Tx I am calling it, from here to here what is the time duration, right. So, how do we calculate? So, Vc is nothing but 7.5, in this case Vs is from 0 to Vs, it is nothing but 15, 1 minus e power minus tau by Rc. So, I will say Tx. So, rather than saying minus T, I will say minus Tx, right. If we calculate the value 7.5, 15 2's, right, 7.5 2's is 15. So, that is nothing but when I take in this direction it becomes 0.5 is equal to 1 minus e power minus Tx by Rc, right. So, when we calculate it, it becomes, I will take this to this direction, this to this direction, it will become e power minus Tx by Rc is equal to 1 minus 0.5, which is 0.5, right. So, minus Tx by Rc is log 0.5, right. So, what is the value of log 0.5? We will calculate it. Log 0.5 is minus 0.693. So, Tx will become this minus cancel, it will become Rc into 0.693. What is Rc? So, previously we have seen R1 is 1 kilo, C1 is 1 micro. So, Rc value is 10 power minus 3, right. So, we will say 0.693 millisecond. So, what we got now? when we see theoretically, we understood that the time taken from here to here is 0.693 millisecond. So, we will keep it, that is Tx, but what we required? We require complete T. So, it is not from 0 to here, we require from here to here, from here to here, charging from plus 15 to minus 15, because it has to go from plus 15 to minus 15. The intermediate stages are plus V reference and minus V reference, right. But actually the capacitor has to charge from discharge from plus 15 to minus 15. Similarly, charging is also in the same way, plus 15, it has to charge from plus 15 to minus 15, but intermediate stages are plus V reference and minus V references. Now, if it is a case, since we are looking into the charging state, so let us consider now we will do this, so that we will get this this T1, this T1. So, later on we will see the discharging there T2, this is T2, I can say T1 plus T2 gives our complete T. Now, so since 1 we have calculated, let me erase this everything except this value. So, everything we are erasing. So, I hope these values are clear. So, the first one is 693 millisecond. So, somewhere I will note it down. So, Tx we got it as 0.693 millisecond, 0.693 millisecond. Now, we are calculating what? We are calculating for T1, because this is T1 we are saying. We are saying T1. What is the value of T1? So, if you want to understand the value of T1 theoretically, now we have to understand our again the charging circuit. How? Now, in this case the charging is not happening from 0, the charging is happening from minus 15 volts, okay. So, I will draw here, the charging is happening from, if I say this is minus 15 and this is plus 15 volts. When I have a capacitor and input voltage is 15 and the ground value is minus 15, if I say, the charging will happen from here to here, right. But because of our beta VSS plus or minus beta VSS or our higher threshold and lower threshold values, the charging can go only up to plus 7.5 minus 7.5. So, we require to know what is the duration of this. So, we require to know the duration, but how do we calculate it? Suppose if I can consider what is the time taken for the capacitor to go from minus 15 to minus 7.5, and that means this particular value, and if I also calculate the time required for the capacitor to go from minus 15 to plus 7.5, that means from here to here, the subtract this value with this value, I will get the time duration of this, right. Understand once again what I mean to say is that, so I will write the bigger picture of this. So, this is the capacitor charging completely, this is minus VSS and this is plus VSS, in this case minus 15 and plus 15, but I need the capacitor at plus 7.5 and minus 7.5, this is minus 7.5 if I say. So, I need to know what is the time required for this capacitor to charge from minus 7.5 to 7.5, isn't it? When we recall back, this was not completely discharged, that means some amount of voltage is already there, that is minus 7.5. From minus 7.5 to it is started charging, but it is supposed to charge till 15, but it is charged only till plus V reference, which is nothing but 7.5 in this case. Now, if I do that, that means I need to know the time duration from minus 7.5 to plus 7.5 volts. So, how do we calculate? We cannot directly put it, it is not a linear circuit at all, it is a non-linear, capacitor charging rate is a non-linear, we can see e power minus t by RC. Because of that, first we have to know what is the time required. I need this voltage, this time period, by the way, this time period. So, in order to find out what we have to do, first we will calculate what is the time taken for the capacitor to go to from minus 15 to 7.5, right, as T C1, and we will calculate what is the time required from minus 7.5 minus 15 to minus 7.5 as T C2. So, the difference between T C1 minus T C2 gives our T1. So, I write down again, this is not so clear. So, the difference between T C1 minus T C2 is nothing but T1. That is what we are interested in. So, how do I calculate T C1 and T C2? So, the same formula, because this is a charging of a capacitor, right, but T in this case is T C1. So, what I will do is that V C is equal to, or V C 1. So, this is V C reference 1, positive reference, is equal to V S into 1 minus e power minus T C1 by R C, right. This is a formula for the capacitor charging. Now what is VC1? VC1 is from minus 15 to 7.5. So, what is the complete voltage, or we can also say how much percentage in our complete VSS, right, how much percentage of complete input voltage. Input voltage range is plus 15 to minus of minus 15, which is 30 volts, and minus 15 to plus 7.5, that is the complete voltage that I have here, right. So, I can say 15 plus 7.5 is equal to 15 plus 15, 30 into 1 minus e power minus T C1 by R C, right. So, if I calculate this value, 15 plus 7.5 is nothing but 22.5, 22.5 divided by 30. So, the value is 0.75, this is 0.75 is equal to 1 minus e power minus T C1 by R C. When we do complete calculation, we will get T C1 as, so I am taking this to this direction, this to this direction, okay, minus T C1 by R C is equal to log ln, right, 1 minus 0.75. So, what is the value of log 1 minus 0.75? 1 minus 0.75 is 0.25. So, log 0.25, right. So, the value is minus 1.38629. So, T C1 is equal to R C into minus cancel, R C1 into R C into 1.3869. R C we have seen, it is nothing but 10 power minus 3 is R C, right here. So, it is nothing but 1.38 millisecond. But is it what T1? No, it is T C1. We also have to calculate T C2. How do we calculate T C2? I am writing it down. So, now V C R2 is nothing but V S into 1 minus e power minus T C2 by R C, right. So, V C R2 is how much? V C R2. So, minus 15 to 7.5, what is the difference? So, 15 minus 7.5 is equal to total input voltage we are applying is 30, 1 minus e power minus T C2 by R C. So, when we calculate the value of this, we will get it as, so 15 minus 7.5 is 7.5, right, 7.5, 7.5 by 30 divided by 30, it is nothing but 0.25, 0.25, sorry, 0.25 is equal to 1 minus e power minus T C2 by R C. When we do the complete calculation similar to this to this side, this to this side, I can say minus T C2 by R C is equal to 1 minus 0.25, which is 0.75, right, log 0.75 by the way, log 0.75. 0.75, the value of log 0.75, right, log 0.75 is minus 0.2872. Now minus minus I can cancel down, Tc2 is nothing but, I am writing down up, Tc2 is nothing but 0.2872 into 10 power minus 3, Rc is 10 power minus 3 millisecond, that is Tc2. So the time taken for the capacitor to charge from minus 15 to minus 7.5 volts is 0.287 milliseconds, and the time taken for the capacitor from minus 15 to plus 7.5 volts is 1.38 millisecond. But I need the time taken for the capacitor from minus 7.5 from here to from here this time. So if I want to do that, it is nothing but Tc1 minus Tc2, which is 1.38 milliseconds minus 0.287 milliseconds, right. The values also make sense. So lower voltage, lower time it takes, higher voltage, higher time it takes for the capacitor. 1.38 minus 287, which is nothing but 1.093 milliseconds. That means the time taken from here to here is 1.093, approximately 1.1 milliseconds, right. This also will keep it aside. Now, so we got one value, this value, right, T1 we got. Now what we need to do? We need to understand about discharging, right, isn't it? Now I am erasing everything, so I hope this is clear. But when we observe carefully, the discharging and charging rate of a capacitor equations are not same, right. So what is if you recall our RC discharge filter, where we would have studied in our previous physics or electronic circuits, right, the discharge, the relation we can write it down as Vc, the discharge rate of capacitor, we can say, if I say this is Vs and this is time and this is Vc, this is Vc, Vc I can write it down as Vs into e power minus t by Rc, right, that is our discharge rate of capacitor, right. So Vc is equal to Vs into e power minus t by Rc is our discharge rate of capacitor. Now I can directly implement this and I can calculate it to know, because this is from full 15 volts to 0 volts, but in our case our capacitor is not fully charged to 15 volts, our capacitor is somewhere here, somewhere around 7.5 volts when I compare with the previous cycle, right. When I see here, the capacitor is discharging from plus V reference, plus V reference in this case is 7.5 volts, right, 7.5, and again is it discharging completely to minus 15 volts? See, is it completely discharging it to minus 15? No, it is only discharging up to minus V reference, that means somewhere in between, and I want to calculate the duration from this reference value to this reference value, this time duration I want, this I am saying it as T2, right. How do we calculate it? If I want to calculate, first I have to calculate what is the time duration required for the capacitor to discharge from plus 15 volts to this reference value, this reference I am saying it as plus V reference, this reference I am saying it as minus V reference, right. So I am saying it as again TDC2, discharge 2, previous one is TC1 one we consider, okay, DC1 from plus 15 to minus V reference, right. And again if I can calculate the time duration from plus 15 to plus V reference, meaning plus VCC to plus V reference as TDC1, since I want to know T2, so T2 I can write it down as TDC1 minus TDC2. Makes sense, right? Right. Now, how do I calculate TDC1 and TDC2? Right. If I want to calculate, substitute the same thing in the equation. So, I will write it down below. Vc is equal to Vs into e power minus t by Rc. So, in this case t I am calling it as TDC1, right. What is Vs? What is Vs? Vs is from minus 15 to plus 15, that is 15 minus of minus 15, 30 volts. Now, what is Vc? Now, since it is TDC1, I want to consider only till minus V reference. What is the discharge time taken for the capacitor to discharge from 15 to minus V reference? Minus V reference is 7.5, right. It is minus 7.5, right, minus V reference. What is the time? So, that means minus 15 minus 7.5, 15 minus 7.5. So, 15 minus of minus 7.5. I want to know the voltage across the capacitor. Oh, sorry. So, voltage across the capacitor is minus 7.5, right, minus 7.5, which is 30, right, into e power minus TDC1 by Rc. So, if I calculate 7.5 by 30, so 7.5 divided by 30, which is 0.25, right. So, minus 0.25 is equal to e power minus TDC1 by Rc. I can say my TDC1 is equal to Rc into log and minus 0.25. So, sorry, this is not 7.5, I am discharging from 15 to, if I see this, I am discharging from 15 volts to minus 7.5, that is when I convert into 30 volts, it will become total 30 minus 7.5, or I can say how much, what is the percentage of Vs in complete 30 volts, Vs, right, what is the percentage of minus V reference in complete 30 volts. If I want to do in that way, I can note it down as, so this is complete 100%, right, 100% is nothing but 30 volts. Now, 7.5 minus 7.5, which is, so this is 50%, then 7.5 volts is how much? 7.5 into 100 by 30, 7.5 into 10 divided by 3, so it is 25%. So, 25%, so this is nothing but 50, so this is 25, right, and whereas this 7.5 is 75. Right now, this is 25% of complete VCCs minus V reference, 75%, right now 0 to 25, 25%, so 7.5, 50%, 0, minus 15 to 25% is 7 point, minus 7.5, minus 7.5 to another 25% is 0, and again from 0 to plus V reference is another 7.5, which is 25%, again another 25% is, yeah. So, I can say this, I can say the relation between Vc and Vs as 25% of Vs is nothing but Vc, right. So, Vs if I cancel, it should be 0.25, some calculation mistakes, okay, 0.25, then it will become Rc into log 0.25. So, which is nothing but 10 power minus 3, okay, I will write it down, so that this space I can use it for TDC2 minus 10 power minus 3 into log 0.25 is how much? Log log 0.25. So, which is minus 1.386. So, minus minus I can make it positive. So, 1.386 which is 1.386 milliseconds. So, the time taken for the capacitor to discharge from plus 15 to minus reference minus 7.5 volts is 1.36, right, makes sense. So, T2 I am noted down as TDC 1 minus TDC 2. So, I got it as 1.386 milliseconds. Now, logically if I see, based upon our logics if I see, so time taken for capacitor to discharge from plus 15 to plus 7.5 should be even smaller than this, isn't it? We will see, we will also calculate that. So, I will say Vc is equal to Vs into e power minus T dc2 by R2 Rc. What is Vc? Now, this is 75% of our full value. So, I can say 0.75%, right. So, 0.75 of Vs is equal to Vs into e power minus T dc by Rc. So, when I calculate T dc2 should be equal to, okay, I will write it down right side, T dc2 should be equal to minus Rc into log 0.75, right. So, which is nothing but T dc2 is Rc is nothing but 10 power minus 3 log 0.75. So, minus 0.287 minus 0.287 minus minus cancel. So, this becomes 0.287 milliseconds. So, makes sense, isn't it? See, when I see the time taken for the capacitor to discharge to minus minus 7.5 value is 1.36, right. It takes longer time to discharge, right, whereas the time taken for the capacitor to discharge to only 75% of voltage, that means plus 7.5 will take very lesser time, right, 0.287. So, the difference value will be 0.287 milliseconds. So, TDC2 is 1.386 minus 0.287 which is nothing but 1.099 milliseconds, right. Now, we got T1 as well as T2. So, when we go back to our circuit, the complete T is nothing but T1 plus T2. So, time period T is equal to T1 plus T2. T1 is nothing but, so I am saying this is T1, this is T2, or T2 plus T1, anything is fine. So, T1 is 1.093 and milliseconds and T2 is 1.099. So, which is nothing but 1.099 plus 1.093 which is 2.192 milliseconds. So, if I want to convert into frequency, it is nothing but 1 divided by 2.12 milliseconds. So, it is okay 2.192 milli, answer inverse I will get 456 hertz, right. We will also see with our experiment, and we also have formula here, 2 is equal to 2 R1 C1 into log 1 plus T is equal to 2 R1 C1 into log 1 plus beta by 1 minus beta. So, how do we calculate? We can calculate in the same way, rather than taking the values we can substitute into, as we have already seen as professor explained in the theory class. So, we can see the same thing. So, if I substitute beta here, beta value is nothing but how much, it is beta is half, right, 0.5 by 1 minus 0.5. So, it is nothing but 1 by 2 minus 1 by 2 and 3 by 2, sorry 1.5. So, when I calculate the value, 2 into 10 power minus 3 into log 1.5 log 1.5 divided by 0.5. So, the value is equal to 2.197 milliseconds, right, the value is equal to this, but this cannot gives us what is T1 and T2 period. But with our logical sense, when we calculate, we also got our T1 and T2 values. We will compare with the simulation, right. I hope this everything is clear. Now we will see, we will do the same thing in our simulation. So we will open our multisim, right. And we have also calculated our Tx, right. We can also see the Tx value too. This is 1 kilo, this is 1 microfarad, right. Now just go to our simulation and a multisim live. Let me create a circuit. Now as we have already seen how to create a circuit in our even older lectures, in our previous sessions. Now we will not see about that, but we have to create this circuit. So this is our circuit, right. So first I have to take our op amp. So I will take 5 terminal op amp, so that we can even provide plus VCC and minus VCC, and I will swap the values, swap the positive and negative just by flipping it, just by flipping the circuit. Then so we have to consider R2 and R3. So I need 2 resistors, one resistor for R1 and other resistor for capacitor, right. Another capacitor, I will reverse the capacitor. Then I need resistor values, which is R2, this is my R2, then other resistance value R3, right. Then what else? Do we need any power supplies? Yes, we need a power supply only to provide voltage to op amp, not to activate our circuit, right. So Astable multivibrator, once you switch on, once you provide a supply to our operational amplifier, it starts charging, discharging, charging, discharging, charging, discharging. We do not require to give any triggering pulse, right. So this should be negative. So I am connecting it to negative value. Okay, and ground, this should be connected to ground. Then I also need one more voltage source to provide to the positive. I am giving it, then I have to rotate. So I will rotate it. Then this should be connected to again ground. Now we made a calculation of beta and reference values plus V reference and minus V reference by considering the supply voltages as 15 and minus 15. So if I want to cross verify with the simulation results with our theoretical calculations, we should change the supply voltages, otherwise it changes complete value. So this goes to 15 and 15. So this is minus 15 we applied at this point, positive 15 is applied at this point. Then what next? R1 and C1 has to be connected, 1 kilofarad, yes, this is 1 kilo ohm, sorry, and 1 microfarad, those are right. So this has to be connected to our this one, and this should be connected here, whereas the negative terminal of an op amp has to be connected here, so that the charging and discharging of the capacitor can be compared with our positive value. Then this will be ground, right. Then after that, in order to provide our saturation, our plus beta V references values, plus and minus V reference thresholds values, we have to connect R2 and R3. Now what values of R2 and R3 we have considered? So, we have considered 10k and 10k and 10k. What will there be any difference if I take 1k 1k? No, because the beta remains same whether it is 1k or 10k, right. So, as per theoretical calculation, beta value is R2 divided by R2 plus R3, 1k divided by 2k, again it becomes 1 by 2. So, whether it is 10k 10k or 1k 1k, or if as long as R2 and R3 are same, these calculations remain same. kilo ohms. So, we have changed everything. So, everything is done. Now, what we have to see? We have to see the time period, we have to see the capacitor charging and discharging, and we have to see the output voltage, right. So, I will put one at this point, capacitor charging, other one at this point. So, green indicates our the capacitor charging and discharging, blue indicates our output. Now, let me save the circuit. Save. I am saving the circuit as Astable multivibrator. Okay. Now, just go to the grapher, run the circuit. Yes. So, I am going to settings, voltage, right. So, I am making it as single trigger, not auto, single, so that only one cycle I can see, right. Now, whether it is right or wrong, how do we know? One thing is, when our input voltage is greater than plus V reference, we should get minus VCC. Now, observe here, when you see here, when the green is the input capacitor voltage goes go more than 7.5, right. See the value 7.48, approximately 7.5, the output is going to minus VCC, right. So, it is similar to our inverting Smith trigger, and again when the input value is minus 7.5, the output goes to plus VCC, right. Output is going to plus VCC, that is clear. But is this the what we require in our Astable multivibrator? No, we require to know, we require to understand what is the frequency of your signal, output signal. That frequency of the output signal entirely depends upon beta R1 and R2 and your RC. What is the capacitor and resistor, charging rate of your capacitor, everything. So, in order to see that, I have to create some cursors. So, one thing is clear, it is working fine. Now, if I want to compare with our results, theoretical results, let me create x axis cursors. Now, if I look into the x axis, one I will make it connect at 0, right, and other I will connect at plus VCC 7.5. So, you can observe cursor 2 value here. Somewhere close to 7.247, somewhere close. Now, what is delta x? Delta x we got 701.61 microsecond, the time duration from the capacitor to charge from 0 to 7.5. This is 7.5, we can see here 7.47 volts is 701 microseconds. What we got? Compare with our result. So, go to this. What is our Tx value? Tx, if you remember, 0.693 millisecond, that is 693 microseconds. 693 microsecond, 701 microseconds, almost close. The difference might be because of this value too, right, because it is not exactly at 7.5. Now, what is other one? Other one is the time taken for the capacitor to charge from minus 7.5 to plus 7.5, right. So, I will make the cursor to be at 7.47 volts, or I can zoom it to, but fine, this is fine. So, the cursor 1 I am placing at minus 7.5, 7.48, so approximately minus 7.5. So, now when I see the time taken for the capacitor from here to here, this time which we considered as T1 in our case is 1.1243, right, 1.1243 millisecond. Just go to our presentation. What is T1? If you observe, this is T1, right, this is the time taken for the capacitor to charge from minus 7.5 to plus 7.5. How much we got T1? T1 we got as 1.093 milliseconds, right, what, wait 1.093 millisecond. See, 1.1243 millisecond, that deviation may be because of the values, or let me zoom in. Okay, from here, oh sorry, I have to do from here to here, 7.48. right, approximately 1.12, 1.093, approximately 1.1. So if I set it properly, since we do not have such a precision in this, you cannot exactly see the value, right. Then what is the other one? We have to know what is the time taken for the capacitor to discharge from plus 7.5 to minus 7.5, the time duration. When we theoretically calculated, we got 1.1 millisecond. So this one from plus 7.5, 7.47, 7.468, 7.48, close to 7.5 to minus 7.48, right, 1.12 milliseconds. We also got 1.1 milliseconds. The complete frequency, when you see, the frequency is nothing but from here to here. So what I will do is that I will make, I will take the cursors on this. So I will keep it, okay. So now the cursors are in C1. I will see from 0 whether we get or not. Okay, I am not getting it, that is fine. To C2. Okay. So 2.241 milliseconds. What is the theoretical value we got? 2.192 milliseconds. 24. The difference because of we have not exactly placed, right. So which means that our theoretical and our simulation results are almost the same, Now we will do the same thing using our board too, using our TI board. We will connect the same thing, and we will see whether we are getting the same responses in our board too, right. So now we go back to our TI board. When we look into our TI board, right, when we see here, so as we have already working on this board from our previous experiments itself. So even now we are going to use this this particular operational amplifier, this op amp, sorry. So this particular op amp, and we know there are different Burr connectors connected to the op amp, right, and we use this platform, this breadboard platform to connect our R1, C1, R2, R3 resistance value, which decides that. Now we will connect the same circuit, we will take the resistance values whatever we require and resistance and capacitance value. So R1 what we consider 1K. So we will take 1K and 1 microfarad capacitor. So in this case we may not require function generator, we need only power supply, this power supply and CRO. We do not need this function generator. So we will take 1K resistor. Now he is connecting it. Then he will take 1 microfarad capacitor. So, where one so we will connect it on a breadboard, then we will make the connections. So, 1 microfarad capacitor should be connected from negative terminal to ground, right. So, even you can see into the our presentation too. About the circuit if you want. Then R2 and R3, R2 and R3 either 1K 1K or 10K 10K we can consider. So, now in this case since we have used 10K, we are going to use 10K. One 10K resistor should be across positive terminal to ground, and another should be parallel across our should be in a feedback path. That means from the output to positive terminal of your op amp. So, you can see the connections. So, we have connected capacitor as well as 3 resistors there, right. One point is from capacitor to 1 microfarad capacitor to 1 kilo ohms, and other 2 resistors which are on the right side are 10K 10K resistors, right. Now, we will take a jumpers and we will connect it to our op amp. So, where we have to connect? One, the junction point of capacitor and the resistor should be connected to the negative terminal. So, the jumper has been connected to, one jumper has been connected to the positive terminal, and other jumper is being connected to the negative terminal, and that jumper is being connected to the negative terminal jumper is connected to the junction of R and C, right. We can see here to the junction of R and C, to the negative of our op amp, right, it is connected. So, other one to the positive terminal, it should be connected to the junction of 10K 10K resistance. So, we can see here. So, to 10K 10K, the junction of 10K and 10K resistor, the jumper has been connected to the positive terminal of op amp. So, that means we made the connections required for that, but we have not even provided the ground terminals. So, we have to give the ground terminals. So, he will take one more jumper wire. So, where is the ground terminal here in the op amp? So, we can take the grounding buck connectors which is on the board here. So, to this ground, so we will connect this ground to the common point there. Right. Then, so we need two common points. Okay. So, now the circuit is ready. So, now what we have to do? We have to provide plus VCC and minus VCC to operational amplifier. So, that we are providing to using power supply to the main power. So, we can see here, even though the board says plus 10 and minus 10, since our calculation we uses plus 15 and minus 15, since op amp can also work for plus 15 and minus 15. So, we are using we are using plus 15 and minus 15, and since here are the connections, the same connections are being connected to the plus VCC and minus VCC of our or to the op amp itself. So, we do not have to take another wires and connect it there. Now, our connections are ready. So, we have to see the voltage across the capacitor, right, and the frequency of the output voltage. For that, we take two channels of oscilloscope. The first channel is being connected at, so the first channel we will connect it at the junction of R and C, which is the negative terminal, to the negative terminal, and other terminal will be grounded, whereas other channel will take the other channel, will connect it to output voltage. So, when we look into the oscilloscope, the yellow, the first channel represents the voltage, the charging and discharging of the capacitor, and the blue one represents our output voltage. Now, the circuit is ready, right. So, now only thing is we have to switch on, we will switch on the oscilloscope as well as power supply, right. So, we got input as well as output too. So, we will keep both in the same plane, so that easy for us to understand. Now, so when we look into our side, we have seen Tx as 0.693 milliseconds, which is nothing but from 0 to what is the time taken to go to plus V reference, and we have also seen T1 and T2 values, and we also theoretically verified. Now, we will see in our experimental way. So, we will create a cursors here. I am going to the cursors. So, I will create type as time cursors. I need a time cursors, and what I will do is that I will take the first cursor and move across 0 line. So, 0 is somewhere here, right. So, cursor 1, if we notice, the cursor 1 will be at 0 volts. So, let me zoom in little bit, so easy. Okay, wait, 2.2. So, at 0 volts. What about the cursor 2? I will select cursor 2. So, towards I am connecting it, reference value, reference is somewhere around 7.5. So, when we see the difference is 720 microseconds, right. So, we got 693 microseconds. Now, other thing is we have to see the complete frequency. So, how can we see the complete frequency? We can directly go to measure channel 1. I can say, so yeah, channel 1 frequency is already set, but I need for channel 2 frequency, I will enable it. So, when we see, we can see the frequency is 439 hertz. So, what we got? 456 hertz, right, almost equal. The difference is because of our tolerances due to our capacitance, probably due to the capacitance resistances, as well as the plus VCC and minus VCC states also. So, since we have applied plus VCC and minus VCC as a 15 volts, but op amp can only go below that particular value, that is the reason there will be small offset variation, right. We can also see T1 and T2, but as we have already seen in the simulation, even it looks the same way even in CRO, right. I hope so we got a complete understanding on how to calculate the time duration, the frequency of our output signal, and how do we compare with the theoretical and practical using Astable. In case, what we can do is that we can consider different other values of R and R2, and we can do the same calculation, and we can compare the results of the results with our simulation and the theoretical. So you can have a look on the complete circuit once again. So, you can see here. So, complete connections are made. Thank you.